Welcome to the video on molecular shape. At this point we have learned to draw Lewis structures, and Lewis structures are how we represent a molecule on our paper. So it's the best way that we can try to draw what the molecule looks like. However, a lot of molecules are not flat. Okay, and so that's not a true representation of the geometry or the shape of a molecule. So we can draw a Lewis structure, and then from that we can determine what the shape would look like. Okay, and if you are taking my course, I have a video on a lab basically doing this, and I actually show you models where you can see the 3 dimensions and everything else. But we're just going to go through the different shapes. And so if you have an atom, you want to look at what's bonded around it. And so another atom or a lone pair is considered a group around an atom. Okay, and I'll give an example here in a second. And the geometry is based on a theory we call it the Vesper theory. And this determines the shape, and basically that theory says that these groups that are around an atom, they are made up of electrons, because we know how atoms bond with one another. And so since electrons have a negative charge, they want to be as far apart from each other as possible. So a molecule is going to assume the shape that is going to put its groups as far away from each other as possible, because they would rather that their orbitals where their electrons reside be as far apart from another orbital, okay, because they repel each other, right? Because negative and negative repel. Okay, and so that's the idea behind the theory and the Vesper theory, and behind why molecules assume certain shapes. Okay, so let me first, before we go through the different geometries, let me just give you an idea of what we're talking about here. So if I have, for example, something like methane. Okay, the first thing I'm going to do is look at the central atom. So a lot of students get this a little confused, but look at the central atom, and I'm going to count the groups around it. So if it's bonded to another atom, that counts as a group. So I have 1, 2, 3, 4 groups. I have 4, you can look at that as 4 different bonds. Okay, and so that works. Okay, if I have this molecule, that's methane over here, and this is different. We have 2 carbons, and this is actually called ethene. All right, if I look at the carbon, okay, each of these, it doesn't matter, we can look at both of them. I'm going to look at this one. I have 1 group, 2 groups, 3. It has 1 carbon over here connected. You do not count double bonds as another group, as 2 groups. It only counts as 1. So this is 1 group, 2, 3. Okay, so you're counting the groups around the atom. So we have 3 groups, and here we had 4 groups. Okay, we're not looking at the number of bonds, we're looking at a group. And so this whole side here, that's considered a group, because that's only bonded to, remember, an atom, okay, or it can be a lone pair, counts as a group. Okay, so speaking of, if we have ammonia, okay, we have 1 group, 2, looking at the nitrogen, 3, and then a lone pair, and it counts as a group, as a 4th group. So that's kind of the biggest mistakes that I see, is not counting lone pairs as a group, and then trying to count multiple bonds as more than 1. Okay, it doesn't matter even if you have, say we have a triple bond here. Okay, this is a good one. Kind of ran out of room here. Let me erase a so lone pairs count as a group, and multiple bonds only count as one group. Okay, so we're going to add this as an example to what we already have. All right, if you look at an atom and it's surrounded by only two groups, those two groups are going to be as far apart from each other as possible, and that's what our Vesper theory says. And so they're going to be linear. That's as far away from each other as possible, and they're going to be 180 degrees apart. Okay, and so that would be a linear geometry. So if you look at CO2, for example, it has two oxygens bonded. So look at the carbon. It's got one group, two groups. Remember that double bond, it doesn't matter. You're just looking at how many atoms or lone pairs are around the carbon. So it has 1, 2. Therefore, it is a linear molecule, and there are no lone pairs on it, so that's it. All right, if you look at this, is called acetylene. This is a triple bond. Okay, if we look at this carbon, we have one group, and then we have two groups, right? If we're looking at this carbon, or we could look at that one, doesn't matter. We have one group, two groups, so this is also linear. So that is its molecular shape. Okay, an atom surrounded by three groups is considered to be trigonal planar and has a bond angle of 120 degrees. So if it has three groups, they're going to orient themselves as far apart as possible, and there's going to be 120 degrees in between them. So an example of this is called formaldehyde, and I'm going to draw it up here just for practice. And if you had models, we have them here at the college, but you could also build these, and you could build with your model kit, and you can see the shapes, and it makes more sense because you can see the three dimensions. All right, and this one's actually, it's planar. It's actually flat. It's in the plane. And so if you were to draw it on the board, it's in the plane of the board. But if you look at your carbon, you have one group, two groups, three groups. So we're looking here. The double bond only counts as one. That's one atom. So just count the atoms around, or lone pairs. And no lone pairs here. So three groups means you have a 120 degree angle and a trigonal planar geometry. Four groups around an atom indicates that you have a molecular shape of tetrahedral geometry, and the groups around the central atom are going to orient themselves 109.5 degrees apart. That's as far apart from each other as possible. This, if you were to build this molecule, you would see something like CH4. This wedge that is darkened, that means that that bond is sticking out in front of the plane. So this has three dimensions to it. So here's sort of a model. So one of the hydrogens is sticking out towards you. Okay, these two hydrogens here are in the plane of the board, but then this hydrogen is behind the plane. Okay, so this would be in front. Okay, so if you're drawing this on a board or paper or whatever, or looking at it that way, these two would be in the plane, but then you would have one hydrogen that sticks back and one hydrogen that sticks front. Okay, and so this is a way that we can represent that by just drawing it on paper. Okay, and so if a molecule has four groups, so here's 1, 2, 3, 4, then it has a tetrahedral molecular shape. Oops. Okay, if you have four groups, but one is a lone pair, so notice back here with methane, all four groups were bonded. There were no lone pairs here. If you have four groups around an atom, but one is a lone pair, then the geometry changes from tetrahedral to trigonal pyramid, or trigonal pyramidal. You'll also see it that way. And it has a bond angles of 107. So this is close to the 109.5. Okay, so here's our example again of ammonia. So we have one group, 2, 3, and then our lone pair counts as 4. And so it has 3 bonded groups, 3 atoms, and 1 lone pair. Okay, so what this is showing you is that lone pairs change the geometry. They change the shape of the molecule. And so if you look here, you have this sort of pyramidal look, and it's not a bond, of course, it's a lone pair. So we have 1 lone pair and 3 bonded atoms, and so we get a trigonal pyramidal molecule. Okay, so you get a pyramid or trigonal pyramidal. Okay, if we have 4 groups around an atom and we have 2 lone pairs, so here we just had 1 lone pair, so that's trigonal pyramidal. If we have 2 lone pairs like water, then we get a bent geometry. So we have 2 bonded atoms and 2 lone pairs. So we have, here's our bonded atoms, and then 2 lone pairs. So we still have 4 groups around the oxygen, but we have 2 bonded and 2 lone pairs. And we get a bent bond angle, okay? And it with an angle of about 105, so still close to that 109.5 that the tetrahedral was. But this is our bent molecular shape. So all of these are put into a table. You can find these pretty much anywhere. And there are actually some more variations that we do in the lab that I also make a video for. I call it a lab just because we work through lots of problems and look at some modeling. But this is exactly what we did. So if we had 2 atoms around that central atom, or 2 groups, okay, and there were no lone pairs, we got a linear geometry, and there's some examples. If we had 3 groups around the central atom and no lone pairs, the bond angle is 120, and it's trigonal planar geometry. If we have 4 groups around an atom and no lone pairs, this is tetrahedral, 109.5. And then if we have 1 lone pair and 3 bonded groups, we get trigonal pyramidal. So we make sort of a pyramid shape there. And then if we have 4 total groups, but 2 are lone pairs and 2 are bonded, then this would be a bent geometry. All right, I hope this helps with molecular shapes, and I'll see you soon.